Hardwood joints. Yes, this is a difficult and an interesting topic. We performed this research in a consortium with 10 partners, 4 research partners and 6 partners from industry. And you see the countries where the research partners are coming from. That is Lermap in France, from Epinal. This is Technical University of Graz in Austria, Karlsruhe Institute of Technology in Germany, as well as Linnaeus University in Sweden. The industry partners, we had 6 industry partners altogether, 3 related to the material hardwood members or structural hardwood members. That is Haslacher Norica Timber. They mainly deal with birch products, within our project at least. Pollmeyer, a German company producing beech LVL. And then Simonin in France, they also deal with hardwood glulam. Now there were another 3 members of the consortium from the fastener industry. This is Schmidschrauben in Austria, Würth Germany and Würth France. They were really different partners. So this is the consortium, 10 partners, but the consortium is organizations and it's people who perform the research, and altogether 21 persons contributed to the results of this research project, Hardwood Joints, and you can see these persons here. They were not all contributing over the whole time, but at least over part of the time. Now, why would you use hardwoods to, let's say, make a structure, a timber structure? There are several reasons. Nowadays, there's an overwhelming use of softwoods if you, let's say, start to create a timber structure. There are several reasons for that. Softwood is readily available, it's easy to work with, and things like that. But hardwood has, for example, a much higher strength. If that's a big advantage, then why don't we use hardwood more than we do today? That is a problem we tackled within this research, but there are hardwoods available. Of course, there are reasons for doing hardwoods or for using hardwoods in the future, and that is, again, for example, also forestry reasons or climate change reasons. We will have much less softwood in the coming decades. The forests are already there, and the young trees are there. We will have in the future much more hardwood trees than softwood trees, or much more hardwood trees than we have today, and we have to use this resource more efficiently. Structural building materials which are available already today, made from hardwood, are glulam members, for example, beech glulam or birch glulam. Even CLT is available in hardwood today from birch, and also beech LVL, which is a product which is quite often, it's not very old yet, maybe 10, 15 years, but which is increasingly used in highly loaded structures. So the material is there. Why don't we use it much more than we do today? Because for a timber structure, it's not just the material you need, it's also the connections, obviously. You need, for example, to connect structural members. You need to connect hardwood member to a hardwood member, or a hardwood member to a softwood member, or to a steel or a concrete member. Of course, there are already rules which allow you to design these or some of the connections, but these rules are, let's say, or lead to quite conservative results with hardwood connections. If you look at the structure, at the capacity, structural capacity of a member compared to the structural capacity of a connection, this is unbalanced today. The member has a very high strength, the connection has a low strength. Now, if you have a member which can carry 1,000 kilonewton and a connection with 400 kilonewton capacity only, you cannot exploit the high capacity of the member. Then what's the use of using hardwood? And that's the start really of this project Hardwood Joint. We want to significantly increase the capacity of connections with structural hardwood members and thereby get a more balanced capacity between member and connection and thereby improve the economy and efficiency of timber structures using hardwood. Mika already has told you the primary purpose of this project, high-performance hardwood structures with connections which are also high-performance connections. And of course, we need design rules. We need to transfer this knowledge into practice so the engineers are able to use these high capacities. The industry partners had a bit of a different view, or a complementary view, you could say. They were asking, how can we set the fasteners, for example? Have you ever tried to, let's say, drive a nail into a beech member? With high probability, the nail will buckle. It's much, much more complicated than to drive a nail into a spruce member, for example. And can the existing fasteners being used? The nail, for example, is there a need to develop new types of nails which are, let's say, which you can use in hardwood structures? Of course, they hope for efficient connection methods, and they hope to get rid of some of the conservatism related to hardwood connections today. Now, how do we go for reaching these goals? First of all, we need to understand hardwood connections because they behave in some aspects differently than softwood connections. Then we need to complete existing knowledge where there are knowledge gaps. And then, where possible, we need to optimize or improve the connections so their load carrying capacity and stiffness also increases. And these three different tasks, understanding, completing, and optimizing, were taken over by different research partners, and the implementation was taken over by all. Now, understanding and implementing was taken over by Linnaeus University here from Växjö in Sweden and Karlsruhe Institute of Technology. Here we looked at really understanding the difference between hardwood and softwood connections. Are there differences? Which differences are there, and how can we explain the behavior? Then filling knowledge gaps, completing information, especially for axially loaded screws. That was performed by Technical University of Graz. And then optimization was done by Lermap in Épinal. They especially looked at the rope effect, at an increased friction between the members to be connected in order to increase connection capacity. And now we'll start with understanding, and I will give the floor then to Elisabeth Cook from Karlsruhe University of Technology. Elisabeth, the floor is yours.
Thank you very much for the introduction. And welcome to everyone here in Skellefteå and also to our online participants. I would like to start our presentation with a few exemplary connections with laterally loaded fasteners that have been investigated. So on the left-hand side, you can see a timber to steel connection with a dowel. And on the right-hand side, there is a timber to timber connection with a partially threaded screw. The loading of the connections is marked with arrows, and both connections were opened after failure and show several signs for load mechanisms that contribute to the load carrying capacity of the connection. So first, there is the embedment of the timber. In the area of the inclined fastener, the embedment strength is reached. Second, we can observe the bending of the fastener, which leads to the formation of plastic hinges. This, of course, depends on the timber thickness. Due to the inclination and the friction between the fastener and the borehole, the so-called rope effect develops and leads to a normal force in the fastener. The rope effect increases the load carrying capacity and is one of the most important load mechanisms for laterally loaded fasteners. So looking at these two shown connections, we can observe a failure of the fasteners in the shear plane, respectively in the area of the plastic hinges for the timber to steel connection. This is a new failure mode that can occur in hardwood connections, and it leads to one of our main aims of research. The current design codes are mainly based on connections made of softwood. So considering the two shown connections, which are geometrically identical here, we can observe differences concerning the deformation of the fasteners. Accordingly, we need a validation for the European yield model for hardwoods. In addition, we wanted to find explanations for the new failure modes, and of course, we need to formulate proper execution rules like fastener spacing. Another main part of our research is the modeling of connections. So using a BOF model, a beam-on foundation modeling, the capacity, so the ductile capacity, not brittle failure modes, but the ductile capacity and the stiffness of connections should be predicted. In a BOF model, the fastener is represented as a beam, here in blue, that is embedded on springs, as shown here schematically. During our project duration, we have conducted research on many different dowel-type fasteners, such as screws, dowels, staples, or nails. The timber members in our test setups were made of beech, birch, or oak, and in addition, we carried out many tests with a spruce specimen to point out the differences between softwood and hardwood. In our presentation now, so in the first part, understanding and implementing, we would like to illustrate our results and our findings on an exemplary connection, and this will be a timber to steel connection with a dowel as shown on the right-hand side here. To understand the different contributions to the load carrying capacity, we need several input parameters for our connection. So a main aspect was the determination of material properties, such as the yield moment and the tensile strength of the fastener. Therefore, 4-point bending tests or tensile tests were carried out. The embedment behavior of the fastener is determined in embedment tests. So these were carried out as full hole tests, as shown in the picture here, or half hole tests. To get knowledge then about the occurring normal forces in the fastener during the lateral loading, there were strain gauges applied, so glued into the dowel. Thus, the normal force could be measured. The last contribution to the load carrying capacity is activated by the axial interaction between fastener and borehole. For fasteners with a smooth surface, it is characterized by friction, and for profiled fasteners, such as screws or threaded parts of screws, the withdrawal capacity can be taken into account. So in order to investigate the two contributions from friction and the embedment, which occur simultaneously in a connection in reality, biaxial tests were also carried out with the activation of the two load directions. So some of these results will be presented now from my colleague Roma.
Yeah. Okay. So the aim of the experimental campaign that I'm going to present now was to investigate the combination between lateral embedment and axial force. So the tests were based on, as you can see here on the picture, on half-hole specimens. And for all series, vertical loadings by means of loading and unloading cycle was applied first up to a lateral embedment, a defined lateral embedment displacement or a defined lateral embedment pressure. And then an horizontal loading was applied, while the lateral embedment displacement was kept constant. So this experimental campaign included two types of steel fasteners, the 8mm hardwood screws and a 12mm steel dowel. And the mechanical response of combined axial and lateral loading of steel fasteners into various wood species were investigated with beech LVLS, oak, birch, and spruce. So that a large range density from 4 to 800 kilogram cubic meter was investigated and was tested. And I'm going to present now some experimental result for a 12mm steel dowel. So here comes the result. So coefficient of friction versus the lateral embedment displacement. So for lateral embedment displacement of around 40 mm, the coefficient measure observed was around 0.8, and this value was observed for each wood species. Just for some birch specimen, very early cracks were observed, which could decrease the pressure surrounding the dowel and thus the coefficient of friction. So similar results were observed for smaller lateral embedment displacement, no differences between wood species, and some birch specimens show smaller coefficient of friction due to cracks. And for lateral embedment displacement around 0.5 millimeters, so with a vertical embedment pressure from 3 to 6 megapascal, so very low compared to the embedment strength of the wood materials. A higher variability was observed that can be explained by the influence of the drilling quality on the measured frictions, which is not a problem for this series because the wood crush and this drilling quality doesn't exist anymore. And so in conclusion of this test, this test shows a nonlinear relationship between the coefficient of friction and the lateral embedment displacement. It's not uniform, it's nonlinear relationship. So that is an input we can use then in the modeling, and we will discuss about that later. So I will now give back the floor to my colleagues.
Thank you. So all of the previously presented parameters are crucial for the understanding of the rope effect. So the following explanation of the rope effect is based on the work of my colleague Michael Schweigler, and I would like to show it to you. So we have three different effects. The first one is the normal force in the fastener. This contributes to the shear resistance of a connection if a part of the fastener is inclined. So this is the case for failure modes with plastic hinges. The normal force in the fastener might be caused by interaction between the fastener and the borehole, so for example the friction, or by a mechanical resistance against withdrawal, like the thread of a screw or the washer of a bolt, as it is shown here in the connection on the right-hand side. The second effect is the friction in the shear plane. So the described normal force also causes a compression component perpendicular to the shear plane. This compressive force leads to a frictional force parallel to the shear plane, which increases the shear resistance of the connection. So this is the rope effect as it is considered in the current design code, so Eurocode 5, with a friction coefficient of 0.25. The third effect is the straightening of the fastener, so additional embedment forces and additional connection resistance can be activated, in some cases, with failure modes exhibiting multiple plastic hinges. So in a bolted connection, the washer acts as an anchor, which induces normal force in the bolt. The normal force causes then a straightening of the fastener, and this generates additional embedment resistance in the area of the plastic hinge. Now we might say we have the understanding of the rope effect, but this arises the question, how can we investigate the rope effect in a test? Therefore, we need knowledge about the occurring normal forces in the fastener during loading. And on this slide, you can see a schematic drawing of the test setup that we conducted. So the side members were made of beech LVL, and the dowel had a diameter of 12 millimeters. Between the timber members and the slotted-in steel plate, there was a space of 0.5 millimeters to avoid friction between these two components. We carried out 5 tests, and the strain gauge now in the dowel is located in the tension zone, so between the 2 plastic hinges that form during the loading. So you can see the borehole and the position of the strain gauge, and in addition you can see an opened dowel. To illustrate our results, I would like to show some load displacement curves on this slide. So in the diagram, the top lines mark the machine load per shear plane, and the lower dashed lines mark the measured normal force in the dowel during the lateral loading. As you can see, we reached about a maximum load of 31 kilonewton in the shear plane, or per shear plane, and until the point of the maximum load, we could record a normal force in the fastener of about 3 to 4.3 kilonewton, which amounts up to 10% of the load per shear plane. The connections reached about 14 millimeters of displacement before the failure was initiated. And all dowels during these tests failed due to fastener failure in the shear plane, as you can see in the picture. With these results, it can be shown that also in doweled connections, an elementary contribution to the load carrying capacity can be activated by the rope effect. So the modeling of the rope effect is a challenge, and the knowledge of the occurring normal forces in dowels is necessary for a validation. So following, an insight into the modeling will be given by Romain.
Okay, so Elizabeth explained a bit the modeling, but I will explain and give more details now. So we have different input, different material properties from the steel fasteners, the lateral interaction, so roughly called the embedment, normal force in the fasteners, and the axial interaction, which can be the friction for the well or the withdrawal interaction for screws. So first, the steel fasteners is represented as beam elements lie on vertical springs. To quantify these springs, you can carry out some embedment test, and you have also axial springs, which are parallel to the neutral axis of the fasteners, and for that you can carry out some residual test or friction test, and you can couple these both springs with some interaction test as I showed before. So the steel fastener now, it's just a very simple beam element with an elastoplastic model, and you can have these properties thanks to bending test or tension test. And last effect of the rope effect, it's the friction between shear planes. So that can be had as well in the modeling. So if we go back now to the experimental result shown by Elizabeth, so you have on the y-axis you have the shear force of the fastener with the full black line, and the gray dashed line, it's the normal force in the fastener measured by the strain gauge. So now we can make 3 different hypotheses. One hypothesis, you have no friction along the fastener, so no interaction between the fasteners and the bore hole. And if we now run the simulation, so we have quite a good response in the elastic part of the curve, but the plastic capacity measured by the beam mount foundation model is so much lower than the one measured during the test. So now if we made another hypothesis, so with a uniform friction along the fasteners, and with no relation between the coefficient of friction and the lateral displacement. So what we can see is the rope effect start to be activated. So we can increase the plastic capacity of the connection, and we can have some normal force. And now if we use the last and third hypothesis with the experimental result that I showed before, so with a nonlinear relationship between the coefficient of friction and the lateral displacement, we can find a very nice response between the beam mount foundation modeling and the experimental result for the shear force. And we still have some, we observe a higher normal force inside the fasteners. So we need to investigate that and need to go further. So now I would like to present another application of the beam mount foundation modeling, which is a proposal of design equation to estimate connection axial stiffness of connections. So, but the first question is why we need that? Why we need new design equation to estimate joint stiffness? So it's clear now timber structure become bigger, taller, and more complex as we saw this mornings, and this problem is also a problem for connections. And for SLS design, for example, joint stiffness, the connection area is really important for vibration analysis, for example, especially for tall timber buildings. And for ULS design, it's important as well to understand and to estimate the good load distribution for each timber member in the connections, and to estimate the brittle failure mode. So, for example, if you assume the same identical stiffness in each shear plane, you will not have the same load distribution if you don't have the same stiffness in each shear planes. And so we need to go further for that. So now, what is included in the current design code? We need something new, but what is included now? It's a very simple equation to estimate the slip modulus of one fastener. And this equation, depending on 2 parameters, the timber member density and the dowel, the fastener diameters. And the question is also, there is no difference with this equation if you have a connection with slotted in steel plate or a connection with outer steel plate. And it's the same for these both type of connections. And we can also ask why maybe there is other parameters which have to be included in this equation. For example, the thickness of the timber members, the thickness of the steel plate, and so on. So the first test and to answer the first step and to answer to this question, the idea is to run numerical simulation with the beam mount foundation model, And for that, different parameters were used for the simulation. So the different density of the timber member, different fastener in a row, different row of fasteners, different distance between the fastener, different thickness of timber member, different thickness of steel plate, and different dowel diameters. And for that, we run simulation with a slot in steel plate connections, and simulation with a thin and thick steel plate, where the steel plates are outer members. So in the thin steel plate, that means the rotation at the end of the dowel are free to rotate. And in the connection with thick steel plate, the ends of the fastener cannot rotate. So that is the first step. So you run simulation, and with this simulation, you can have numerical load slip curves. And from this load slip curve, you can extract the stiffness. And then you can build a database with different stiffness, different geometry, different density, and so on. And the last step is the second step, sorry, is to do some nonlinear regression analysis of the database to find the exponent of each parameter which is important to estimate the stiffness of connections. So with this nonlinear regression analysis, you can create 3 different equations for these 3 different configurations of connections. And so you can estimate the stiffness for these 3 configurations. And then you can also use this equation to estimate the stiffness on multiple shear planes connections. So the last step is to validate this different design equation proposal. And for that, an experimental database was used, including different wood species, products, dowel diameters, a number of fasteners, and 2 shear planes or multiple shear plane connections. So that is my conclusion for this part, for our part, with KIT and Linnaeus University. So I will just make some summarize of that. So the first was to check if the current design equation in the European model are suitable for hardwood connections. So yes, in general. So we can use this equation, and we can improve the code with new failure modes. And we can also use the beam mount foundation modeling to predict the load carrying capacity and the stiffness of connection with the beam mount foundation model. And the rope effect can be predicted as well with the model. So we have looked now on joints with laterally loaded fasteners, and I will now let the floor to my Austrian colleagues to present joints with axially loaded screws.
Thank you, Romain. I began with the characteristic of a screw joint in the timber. Obviously, there is a timber bar element with a grain and main bearing direction. Try to use. Of course, we need for a screw to join some outer connection elements. And the fastener we concentrate on is the screw, or more precise, the groups of screws. The screws you see here are inserted with an angle to the grain. Further, there is the loading direction, and the screws have a really high bearing direction, bearing capacity in axial direction. There is a variety of joint design, parameter settings, and loading situations. And now the challenge is to define logical, general, and simple design rules for all of them. Such design rules concern geometric minimum conditions and execution rules. For example, some in-between spacings, minimum distances, and so on. The actual valid design standard Eurocode 5 regulates these connection types. Additional, we have several screw approvals, and partially they also allow end grain joints. The strategy for a safe joint design in Eurocode 5 is, on the one hand, to define minimum geometric and execution conditions, for example, like the torsional resistance of the screws, pre-drilling, and then named spacing or distances. Diverse ethers allow the use of self-tapping screws without the need to pre-drill, and usually they allow a tighter grouped design. On the other hand, for the knowledge of the joint capacity, we have to consider the failure modes at the insertion and at the loading. We avoid the splitting failure or torsion failure by the insertion with these given conditions. And to get the resistance, we have to verify all possible failure modes. They are, for example, withdrawal, as pulling out the screws of the timber, a screw tension failure, a block shear failure of the entire group, or, for example, a row shear failure. The first modes have a similar behavior as the single screw, so it's easy to determine the single screw capacity and multiplying them with the effective number of screws. The lower one are brittle timber failure modes and more complex in their behavior. Here I show you a load deformation curve of joint connection, and if there is a withdrawal failure, you get good resistance and so on, and if you have the same group size but you use a tighter group design, it's possible that you have block shear failure with a reduced resistance. This is one problem of these brittle timber failure modes, and additionally, Eurocode 5 doesn't contain any verification model for these brittle timber failure modes. Actually, they are under discussion and always with focus on softwood species. All rules for screws focus on softwood species. The question is now, are the given conditions adequate for application in hardwoods? Next question, there is the higher density of the hardwoods, followed by a higher insertion resistance and bearing capacity. Can we use the same arrangements and the same screws? Are there limits in the screw capacity? So meanwhile, we have screws with partially optimized properties for use in hardwoods, even self-tapping screws. So the safe insertion can be easily controlled by doing so, and producers and our experience show that the insertion works. And the third question is, due to the unsolved handling with these brittle timber failure modes, we suggest to prevent them by defining additional conditions. You see, we need to review the given regulations on hardwood and investigate their impact on the failure behavior. We did a lot of experimental investigations within this Hardwood joint project. And from the manifold application possibilities, we concentrate on 3 different joint types. Sorry, that's not back. Yes, I found it. A connection with loading perpendicular to grain. A tension lap joint with an inclined row of screws, and an end grain joint. As material, we concentrate on hardwood species, birch and beech, and we tested them in form of solid timber, glulam and LVL. We used self-tapping screws as worst case scenario for possible initial crack building. We varied the parameter settings, like the spacing in between the screws, the dimension, the insertion depth, and so on, the group size. And finally, we related them to the failure modes. And presenting now the main results, I come back to the questions. Are our screws and the minimum geometric and execution conditions adequate for our axially loaded groups of screws? A good note, a good thing. Yes, generally they are. And the second important question, can we suggest minimum condition, geometric and execution conditions to avoid these brittle timber failure modes? Even here the answer is yes, but we have to differ between the joint types with a separate view on end grain joints and more or less all the others with insertion from lateral timber side. We have to differ between the timber products LVL and glulam. And we have to consider there are different regulations according to Eurocode 5 and diverse ETAs. And additionally, we define some additional parameters, settings for the end grain joints. And in addition, there is some more specifying for which, if you differ between wish wobble and screw tension failure. So that's in the end easy that I can say yes, that works. Screws in hardwood works, and so we know about we learned what's the short-term behavior of these groups of screws, and we know there are some long-term effects in the timber regarding the load intense and the climate conditions. So what's about these long-term effects named as duration of load effects, and this tells us now my colleague Michael Stettner.
Thank you, Ursula. Hello to everybody. My name is Michael Stettner, and I would like to make a switch now from the short-term testing to the long-term testing. And as Ursula said, it's also known with the duration of load effect of self-tapping timber screws. And let me now start with the first point of the agenda, why I'm doing the investigations due to the DOL effect. And let me show you first of all this beautiful equation which you all know to calculate the withdrawal capacity of self-tapping timber screws. And there are especially 2 parameters where the DOL effect is anchored, and this DOL effect is anchored once in the K-mod, as we all know, and also at the K-ax. The K-ax is described throughout this bilinear model, where we can see at 0 degrees K90 value of 0.3, and at 45 degrees we can see this K90 value of 0.1, and there is no differentiation due to the 90 degrees, so also the K90 is 1. Why is now the K90 value at an angle axis to the grain of 0 degrees at 0.3? It's because of the fear that there is a very high DOL effect. And we know from short-term investigations that we can gain a very high value of the K90. It's about 0.7. And as I mentioned, we have the K-mod factor, and the K-mod factor considers the product, the joint, the service class, and the load duration class. I would like now to show you the test setups. I have 2 test setups. On the left side you can see the test setup for the single screw, and on the right side you can see the test setup for the groups of screws with the group size of 4 and 9. And on your very left hand side you can see the different screw types which I'm using. Furthermore, I use spruce and beech and also birch, and as I said, different screw types. And as I mentioned before, I have also a variation in the angle axis to the grain with 0, 15, 30 and 45 degrees. Let me now show you such a preliminary DOL chart. This is a chart now for spruce, where I consider the reference screw and the prototype 1, which is the hardwood screw. And let me first of all explain this chart. You can see here on the abscissa the time in a logarithmic scale, and you can see on the ordinate the load level, which can somehow interpret it as the K-mod factors. You can see here each single dot is one long-term test. And of course I added here a trend line, and you can see the current time in testing. So I'm testing almost 4.7 years. And at the very top you can see the load duration classes: instantaneous, short, medium, long and permanent. So in the next step I take then on the conservative side the K-mod factors from the chart, and I have also some values for you. And if we now have a look to the next table, you can see these values for the load duration classes for the different screw types. And I have also added the K-mod values from the current standard, the Eurocode 5, and we can see that there is not that big difference due to the K-mod factors, which makes me quite happy, because now referring to the bilinear diagram again, as I said, we can see here the 0.3, and now I can make a suggestion. Okay, I have to say the angles with 0, 15, 30 and 45 degrees, and I have to say and would like to mention that I started investigations with 90 degrees just last week, and now I would like to make the suggestion that we can increase the factor K90 from 0.3 to approximately 0.6 or 0.7, so we increase the performance of more than 100%, and this is very nice. So at the end, I would like to repeat our question if the geometric minimum and execution conditions are also applicable in the case of DOL, and I have to say yes, they are, because I observed in each single long-term test a withdrawal failure. So this is very good, and I can provide K-mod factors for the single screw already, and the K-mod factors for the groups of screws are now in the computing, and I'm looking forward in the near future that I can say something about the K-mod factors for the group of screws. So let me now make an overall conclusion according to the presentation also of Ursula, and I would like to ask again the geometric minimum and execution conditions if they are adequate for hardwood joints in short and long-term testing. Yes, they are. And which is good is that we have the target failure modes also in the single screw behavior, and so we can transfer our results to the group of screws. So we were now talking about the dowel type fasteners, and now I would like to ask if there is some other opportunity to increase the stiffness and the capacity, and I would like to invite Annabelle, which is a French colleague of mine. Annabelle, please.
So thank you, Michael. My presentation will focus on the development of an innovative joint, the shallow grooved joint. First, let me explain what is a shallow grooved joint. It's the assembly of grooved planks, so you have a picture here, and you also have some samples of grooved joint here. The grooved planks are held together by screws, and at the wood elements intersection, the shallow grooves fit together. Grooves are in contact. Their function is to transmit the shear forces, and since hardwoods have higher properties than softwoods, use them increase the stiffness and capacity of these joints. So, the main idea here was to increase the friction between the wood elements with shallow grooves. But the development of grooved joints doesn't only come from this idea. Indeed, the first idea was to create expanded structures in 3D by piling planks. These structures consist of planks with the same section, piled and connect with shallow grooved joints. This structure that you can see here consists of planks with consists of crossed planks, and if we had insulation boards, it becomes a wall that can be used for a building. As we use screws, the structure is dismountable, so at the end, the planks can be reused for another purpose. Shallow groove joints have been also developed with the idea of a robot-based production of the structure's elements. So I presented you the main ideas that led to the creation of shallow groove joints. Next, the scientific and technical obstacles that appear to be able to build with this joint. The first obstacle is machining. Can it be done for all hardwoods? The second question is about the screws. How many do we need? What are the design rules for them? For example, the minimum edge distance. The third question is about load carrying capacity and stiffness. Shallow groove joints can have different geometries. The planks can be crossed at a variable angle. So we need to establish design rules for load carrying capacity and stiffness as a function of the angle between the planks. The last obstacle is the moisture influence. It's really important with timber joints. The stiffness and load carrying capacity depend here on the contact between the planks, between the grooves. For example, in this picture, you can see the effect of shrinkage. There is a gap between the planks. So the question here is, what is the influence of the moisture content variation on the mechanical behavior of the joint? Let's start with the machining. The grooves are machined at Lermab by a gantry robot with a specific tool that you can see here. As said before, the planks can be crossed at a variable angle. So the grooves have to be done in different directions from the grain direction. In the longitudinal direction, all species can be machining. It's the same with an angle of 45 degrees between the groove direction and the grain direction. For grooves in the transversal direction, perpendicular to the grain direction, machining is possible for beech, birch, and oak. But we still need to find optimal parameters for beech LVL. Now, for the screws, pull-out tests were done with beech, oak, birch, and beech LVL with a screw of 5 mm diameter. Pull-out tests with one screw were done to characterize the withdrawal strength of the screw for each piece. Pull-out tests with 4 screws have been carried out to study the influence of the proximity of the screws. Therefore, find the minimal distance between the screws, that it's about 5 millimeters. Also, with 4 screws, tests were done with different configurations to find the minimal edge distance for each species. To investigate the mechanical behavior of the joints, shear tests were done with different angles between the planks. For the configuration at 0 degree, the wood elements have the same grain direction. For the 90 degrees configuration, planks are crossed perpendicularly. And there is also a configuration with an angle of 45 degrees between the planks. Shear tests were done for beech, oak, and birch, with 1, 4, or 6 screws per shear plane. Now let's look at a test at 0 degree with beech, with 6 screws per shear plane. You can see 3 wood elements with the same grain direction held by 12 screws, 6 on the left and 6 on the right. But the position of the screws is not symmetrical, so that minimal distance between the screws and minimal edge distance are respected. You can see that the middle element wood is loaded. And at the top, you can see the failure of the grooves. So let's have a closer look at the results. I'm going to present you test results for 0 degree shear test for beech. The graph shows the load as a function of displacement during testing. The black line represents the load for a joint with 4 screws per shear plane, and it's a joint without grooves. It's just to have the behavior of the screws. Now, the blue line is for the same joint, but with grooves. So when we compare the curves, we can say that the load carrying capacity of shallow groove joints depends on the shear strength of the grooves. In this configuration at 0 degree, these are transversal grooves. Therefore, the joint capacity depends on the longitudinal shear strength of the wood. The shear can only be transmitted if the planks are held together. So we need screws. But the groove's friction limits the number of screws. For example, with 6 screws per shear plane, there is no huge difference than with 4 screws. And to characterize the friction between the grooves, tests with 1 screw were done. Now we can have a look at 90 degrees shear tests. Pay attention that the displacement scale is different, but the load scale is the same. And you can see that it's the same behavior as for 0 degree tests. But the load carrying capacity is lower. Like for 0 degree tests, there are transversal grooves. But there are also longitudinal grooves. Therefore, it's the rolling shear strength that governs the behavior of the joint. The rolling shear strength is lower than the longitudinal shear strength. Until now, all shear tests were done at a 12% moisture content. But what will happen if the wood loses or gains moisture? To quantify the influence of moisture content on groove joint stiffness and load carrying capacity, shear tests were done with moisture content variations for 2 configurations and 2 hardwood species. Let me present you some results for 0 degree shear tests for beech. This graph shows the load carrying capacity of groove joints with 4 screws as a function of the moisture content variations. That means that at 0%, our tests done at 12% of moisture content. Joints were assembled at 12% and tested at 12%. On the left, there are tests with joints that have lost moisture content after the assembly. So there has been shrinkage between the wood elements. At the opposite, on the right, there are tests with joints that have gained moisture content. So there has been swelling. From these tests, we can characterize the influence of moisture content on the load carrying capacity. And it's possible to do the same for the stiffness. But for both cases, we can't conclude when joints gain moisture content. But we can establish a law where there is moisture content loss. For example, at minus 8%, there is a loss of 50% of the load carrying capacity. And let's take a closer look at the sample. Before testing, as expected, there is a gap between the grooves due to the shrinkage. And after testing, you can see the failure of the grooves, as before. All tests I presented, shear tests at 12%, shear tests with moisture content variations, and pull-out tests, were used to define design rules that I am going to explain briefly. The joint consists of an element with transversal grooves. The grooves are perpendicular to the grain direction. To this element, a second element is screwed. The angle between the grain direction and the grooves direction is variable for the second element. In this case, the load carrying capacity of the joint is a minimum of two values. The first one depends on the cross surface and the groove's shear capacity. The second value defines the screw's holding capacity and takes into account the friction between the screws. This friction has been characterized by shear tests with one screw. Let's go back to the groove's shear capacity. These depend on the groove's shear strength at different angles from the shear test at 12% of moisture content. And it's corrected by a factor to take into account the moisture content variation influence. Now for the stiffness, with the same joint definition. The joint stiffness is the sum of the stiffness from the wood and the stiffness from the screws. The first part depends on the cross surface and on groove stiffness of each element. This stiffness can be calculated with this expression, which depends on the stiffness of the longitudinal and transversal groove stiffness. We need this expression to take into account the variable angle between the groove direction and the grain direction of the second wood element of the joint. Longitudinal and transversal grooves stiffness are given by shear test at 12% and those with moisture content variations, like for the load carrying capacity. Now, some structures are already built with shallow groove joints. For this bike house, you can see a transparent wall with shallow groove joints with glass. Beside and below, those are also walls with groove joints, but with insulation boards. Shallow groove joints can be also used to build columns and lattice beams. All these elements are in pitch inside the building, and outside of the back house, as you can see at the right top, the lattice beams are in oak. Below, there is a bus shelter built with a structure in oak and a large cladding. So this picture concludes my presentation, so thank you, and I give the floor back to Professor Blas.
Well, you just followed the presentation of the research results of hardwood joints, understanding, completing, optimizing, and implementing new insights into hardwood timber connections. Just summing up shortly, really, are the present design rules suitable for hardwood connections? In principle, yes. However, we need to look at combinations of wood species. We cannot have the same rules for all species. And we need to include new failure modes, especially breaking of the fasteners, which was not observed or was never observed in softwood connections. Then we have a big gain using the Beaumont foundation model. We can now much more precisely determine load carrying capacity and the load slip curves, and that means we can determine slip or stiffness values of connections, which are very roughly determined up to date. The part completing, yes, we can now implement hardwood joints with axially loaded screws, and obviously the long-term effect is much less severe than anticipated. We look at the optimization and the implementation. Shallow grooves can considerably increase friction in shear planes, and that leads to new chances of having high-strength connections in hardwood joints. So the industry partners, this is a repetition of the beginning. They hoped how they would learn how to set fasteners and if traditional connectors can still be applied. And they wanted, as a result, efficient connection methods and get rid of the conservatism around the design of hardwood connections. Now, they thought in the beginning they were just looking at the fasteners and could solve problems just by solving problems with these fasteners, but we need to have a closer look at the surrounding conditions, for example, climatic conditions during storage, transport, or erection. And also we need to have a look at very good production and processing conditions. This has to be considered as well. We also need, of course, the transfer of the research findings to practice in order for the engineers to be able to use them. And therefore, we need an application brochure where the results are being gathered and given to practicing engineers. And that leads me again back to Annabelle, to the panel discussion.
Thank you, Professor. Thank you. I will now begin the last part of our presentation, the panel discussion, and it will begin with a quiz. So, you have seen this slide in the beginning. It's all the people involved in the hardwood joints project. 21 very nice people. If we put everybody in a basket, a big basket, it will weigh 1.6 tons, and that represents 16 kilonewtons. So now, have a look at this groove joint. So I have one here, for example, so you can see the size of the joint. This joint is in beech, with 4 screws per shear plane, so it's 8 screws in total. Okay. And now I will ask the question, but it's old school quiz, so you will have to lift your arm. It's not an application, sorry. So the question is, how many baskets with a team members can be lifted? You have 3 options: 0.1, so 2 people, it's not very hot, 3.4, and 11.8. So who is for the first option, 0.1? You don't believe in this joint. Who is for 3.4? Some people, okay. And for the last choice? Yeah, you're good. You follow the presentation. Yeah, it's a good answer. And if we put this little joint here, so you can see here, I don't know if it's the little joints. The scale is different because this little joint can support a lorry of 90 tons. That's what it means. So Ursula will ask the next question.
I even have such a question for you. You see here an end grain joint with a glulam of beech, and there were inserted such screws, 19 of them. Now, as you see, the loading is parallel to grain. You see the arrow for the force direction. The question is now, how many lorries can be lifted with this connection? You have the possibilities 0.6 times, 2.8 times or 1,000 of them. So who is for the first solution, 0.6? Okay, I see some hands. Who decided for the second solution? Okay, more. And who thinks there are 1,000? It's the right answer. Okay. It's the second solution, right? Done. You can lift, which is it's the relation, the right relation. You can lift nearly 3 lorries with this connection type. Okay. We prepared another one.
Okay, a question to the laterally loaded connections. It will be a more challenging one, but I believe in the audience, so you can see a joint made of beech LVL. We had 2 times 4 screws, so groups of screws. The loading was in grain direction, but the screws were inserted perpendicular to a grain. So here you can see the connection in detail. So we have 8 screws on both sides. So the question is now, what is the position of the lever arm in order to break this joint? So all the engineers, please go ahead. We have the basket on the right-hand side with the 16 kilonewton. I will give you some help. So we are looking for the ratio of B to A, and we have 4 options: 0.2, 1, 19.9, or minus 6.2. So please go ahead. Who is for choice number 1? Maybe someone needs time to calculate. Okay, we go over option number 2. B to A is 1. Then number 3, 19.9. Okay, I can see a few hands. And who is for the last option? Oh, somebody. Okay, interesting choice. So, of course, it is option number 3, and this joint could carry 320 kilonewton. Okay, I hand over to the last quiz question.
Yeah. Okay. Okay. Last question for our old school quiz. So I will try to be more serious than my colleagues. So how much time do you think we need to run simulation of this steel-to-timber connection with 2 rows of 6 fasteners?
And which computer do you have?
This computer. So, first answer. Yes, for this one I need my French accent. The time for a French talks about food per day, or drinks, yeah. The time for a German to drink a mass of beer. The number of Wiener Schnitzel consumed in Austria per inhabitants per year. Or the time it takes to understand IKEA instruction to assemble a furniture, but very simple furniture. So I will just give you some, the answer now. So for the first answer, so 1,440 minutes, so 24 hours per day. So who think is the good answer? Yeah, okay. So the time for a German to drink a mass was 0.5 minutes. Yeah, I saw some German people too, so they want to define their own cliches. So, yeah. The number of Wiener Schnitzel, so it's 200 per year, inhabitant per year. That is the official number. Yeah. So 200 minutes. And the time it takes to understand IKEA instruction, so 4 minutes. Yeah. So yeah, we need 4 minutes to run this kind of simulation with the beam morpholation modeling. So yeah, that's concluding our presentation. So now we can have some real questions together and start our panel discussion.
Okay. Which one would you like? This one? Okay.
So are there questions? Yes, please. Daniel? Yeah.
Thank you. Dan Ridley-Ellis, Edinburgh Napier University. It's a quick question, but not necessarily a quick answer. So with softwoods, they're all quite similar, and we have this density versus whatever we want to predict approach. Hardwoods are more varied. Not all of the density in hardwoods is the same stuff. So do we need to categorize different kinds of hardwoods? Do we need to limit what you've done to certain kinds of hardwoods? Or do you just need more research money?
The last answer is always the right one, of course. No. Who wants to answer?
Yeah, I think we can create different group of hardwoods, but that could be more difficult for the code or for engineers. So I think we can keep softwood, we can keep hardwoods, and some kind of hardwoods can be assimilated to softwood. For example, birch is very close to softwood properties. So I think we just need to split into groups, hardwood, softwood, but put some hardwood in softwood, and yeah. Just keep it simple, I think.
And I think we have also to consider the product. We are always talking about the wood species, but we investigated different products. And one of them is the Baubuche, the beech LVL, and there are some things which you have to consider if you use some different products or glue laminated timber of birch, for instance. Yeah.
I can also answer for the screws. If you use screws in these hardwoods, the one we used with about 8 or 10 millimeters, you need only a really shorter insertion length to reach screw tension failure. So you are more with a lower length, you are on the limit of the screw. Then you have only increase the number of screws. So that's maybe some difference to even to softwood.
Okay.
My question relates to the, what is it called, the shallow grooved connections with screws. You showed a very interesting diagram. It was a force displacement diagram, if I remember correctly. You had the case, one extreme case where you had the 4 screws and no grooves at all, where you got a lot of slip, so a lot of displacement at not so much force. And the other case where you had a rather steep increase of the force and not so much displacement was obviously the one with the grooves. So I'm thinking, okay, to put one on top, yeah, the absolute extreme case would be if I would glue this connection. So if I would put glue in between. I mean, looking at these grooves, I have a little bit of a fear that once you try to assemble this on site, so you make the grooves in the shop, you assemble it on site, and I know how aggressive the, in particular, beech is in terms of swelling and shrinkage. Could it happen that it wouldn't fit on site anymore, etc.? So my question is, would there be some kind of a glue that is not absolutely rigid, but which would behave in some kind of an elastic way, but strong enough that you would get a rather good connection, because it would make life probably easier on site, in my imagination.
Yeah, you're right for that. For the production, we need to have a moisture content, an initial moisture content always the same for the production, and then the glue, it's a good idea to increase the friction, of course, but we are using screws that we can also reuse after the planks. So it was the other idea to use this kind of groove connection. And I'm not sure I respond to your question. No.
Okay. We only have time for another question anyway.
Okay.
Simon Eicher.
Okay.
very good research and very good presentations, and not only the jokes at the end. I do not understand very much from mechanical fasteners, maybe a little bit from bonding. And mechanical fasteners and bonding have not much similarity, but one. That is the friction effect and the bonding. And my question in detail refers to the rope effect of fasteners which are not held by washers and which have a smooth surface. Is there any knowledge on the long-term behavior, on the long-term slip behavior under varying moisture contents, which is especially more important in hardwoods than in softwoods, as they have a different shrinkage aspect? So, very discreet, my question is it like this, that the rope effect could reduce more than, for instance, the embedment capacity in long term and under varying climate and load? So, very long, but...
Very easy answer, we don't know yet. And there comes the additional research money into play. Okay, yeah. Mika.
More, and then we need to stop.
Will it be harder to design very ductile connections in hardwood? For example, in the case of structural robustness, progressive collapse, we want very large rotations and a lot of ductility in the connections.
Well, I could answer it for the laterally loaded fasteners. There we can observe with the larger deformations the failure fastener. So for small displacements, I would say it's similar to softwood connections, but with the larger displacements, there are larger normal forces in the fastener, and then we have this failure mode. But it might differ for other loadings.
Yeah, I think the screws, there are some limits in ductility, maybe. We have really stiff connections, and but if we want to provide some ductility, we have to include the steel design of the connection elements, and to maybe that we bring there some ductility in to the connection.
Especially at the axis to the grain angle of 0 degree, for sure. Yeah.
Okay, thank you, and once again, big hand to the Hardwood.